right, so this is the last hour of Physics 1A for March 15th. Okay, so we want to solve this projectile problem. It says you throw a ball from your window 8 meters above the ground. The ball leaves your hand. It's moving at 10 meters per second at an angle of 20 degrees below the horizontal. How far horizontally from your window will the ball hit the ground? And we want to ignore air resistance. So let's try to draw an actual picture of what's going on right here. So you're at a window, so we'll say you're in some kind of building. It's shaped something like that. And you've got, we'll draw a line right here to represent the horizontal. Because it's saying that, oh, the window is 8 meters above the ground, so we can write that out on our picture. And you've got a ball, and it is shot downwards, like this. And it says it's an angle of 20 degrees below the horizontal, so that looks somewhat okay. Black, there it goes. So that's the kind of launch angle of the ball. So here's our ball. It's launched along an angle like this. And you know its initial velocity. I'm not going to write as much on the picture here because I think that looked really bad last time. We'll just call this V initial right here. The angle we're just going to call theta inside of here. And then above here I'll just say theta is 20. And V initial is 10. You could call this negative 20 if you really wanted to. Maybe we should. What do you all prefer? Would you prefer positive or negative 20? You all want to do negative? Okay, let's do that. That'll actually... Yeah. Okay, so this is going to be negative 20 then. We use theta equal to negative 20. All right, so we want to find how far horizontally from the window will the ball hit the ground. Okay, so we need to add the ground in here. Which will be down here. I don't know how far we need to go. Maybe to like right there. Line it up with that. So the path that this ball will take, I'm just not going to do a very good job of this. It's going to fall along some path like this, I think, and then this distance down here will be delta x, and that is what we're trying to figure out. So in order to do these kind of problems, you always need to define an xy coordinate system. I'm going to call this the x direction, and we'll call this the y direction. Something to keep in mind in problems like this, you are more than welcome to make down positive, and in this problem it would actually make a lot of sense to make down positive, but we're not going to do that. Okay, so after deciding what the x and y directions are going to be in your problem, the next thing that you want to do is you want to take your velocity vector and you want to break it up into components. We're not going to be doing the physics of just that vector. We're always going to be breaking things up into components. So the x direction is going to point this way. That's going to be the x component of the velocity, and then our y component of the velocity is going to point down this way. This. And then we'll just say that on top of this, that this is going to be Vx, and that it's going to be equal to V initial times the cosine of theta. And this is going to be Vy initial, and that's going to be equal to V initial times the sine of theta. All right. Now our goal is to find delta x. Let's see if we have enough information to just look at the x direction. So in our x direction right here, what we know is that there's three variables that we care about: delta x, Vx, and t. We do not know what delta x is. We do not know the time that it takes for the ball to get to the ground, but we do know what Vx is. Vx is going to be equal to V initial cosine theta. Plugging in numbers, that's going to be 10 meters per second times the cosine of negative 20. And that'll give us a number. We'll write it down here. Vx is equal to 9.3 I guess we just call it 9.9 or 9.4. All right, that's our X information. We can pretty clearly see that we only have 1, 2, 3 pieces of data. Actually, sorry, that's not even true. We only have 1 piece of data, and we have 2 unknowns. So we really can't do much with this. We need to have some more information. That's going to come from the y direction. In the y direction, what we've got is delta y, ay. We know what the acceleration is. It's going to be negative 9.8. What else do we have? We've got Vy initial. And Vy initial in this case is going to be equal to 10 meters per second multiplied by the sine of negative 20. And then Vy and t. We don't know what these are. If we calculate what this is, it's going to be a really small number. I get negative, oh, it's actually not that small, negative 3.42. Okay. What else do we know? What's delta y equal to? It's not 8, it's negative 8. Yeah, it's negative 8. We're going downwards, right? So just as a reminder of how you can do this, in case you get confused, you pick a point to be y equal to 0. Like, let's say that I pick this point right here to be y equal to 0. If I choose that, then this point at the top is going to be y equal to 8, right? And then if I say delta y is equal to whatever the final y coordinate is minus the initial y coordinate, the final y coordinate is 0 minus the initial y coordinate, which is 8, and you get negative 8. That's how you do that, okay? Or you just say it's moving down, so it's moving down and up is positive, so delta y is negative. However you want to do it. Now, if you notice, if you look at the y direction right here, do you see how every single thing that we have is negative? The initial y velocity is down, so it's negative. Gravity is negative, and delta y is also negative. So can you all see why that it might make sense to just make down positive? Because then everything would be positive, basically, right? So it's up to you if you want to do that. You don't have to. Yeah. All right, so we got all that information, and luckily we can look over here and we can see that we have 3 pieces of data over here that we know, right, in this table. And anytime you know 3 of these, you can find the other 2. Now, which one do we want to find? Do we want to find the final velocity, or do we want to find the time, and why? Time, yeah. Because if we find the time here, it's going to be the same as the time in the x direction, so we can use it to solve for what we're trying to solve for, which is the displacement here. Okay, so let us write some things down to solve this. So we need an equation that has delta y, ay, vy initial, and t. If you check your kinematic equations, that equation is going to be this one. I always think of this one as being the one we use the most. It almost needs a name because we use it so frequently in physics. And we just need to solve this equation for time. So delta y was negative 8 meters. Vy initial was negative 3.42 meters per second. Apologize. It just loves putting those little lines on the force. I don't know why. And I guess if I write my force like that, that won't happen. 3.42 negative times t. And then minus, or well, we'll write it like this, 1/2, and then negative 9.8. Of course, we want to solve this for t, because t shows up as t to the first power, t squared, and technically this is t to the 0. This is a quadratic equation that we can solve. So what I'm going to do is just move all the stuff on the right-hand side to the left-hand side. So the first term, we'll write it like this. So we want to write this term first, right? So 1/2 of 9.8 is 4.9, right? So I'm going to write this as 4.9 plus 3.42 and then minus 8 equals 0. All right, that means we need to use the quadratic equation to solve this. Can you all do that? I'll write it out here, but solve it however you solve quadratics. You know, if you've got a program in your calculator, if you want to plot it and find the intercepts. Whatever you want to do. I'm going to write out the quadratic here, though. So t should be equal to negative 3.42. I'm not going to put the units in here because I just think it makes it harder to read. So plus or minus the square root of b squared. It's minus 4ac, right? So 4ac is actually going to end up being positive because there's a negative sign there and a positive sign here. So it's going to be 4 times 4.9 times 8. And all of that is divided by 2 times a, which is 4.9. And we'll get two answers here. We'll have to decide which one we want to use. Usually when you do this, one is positive and one is negative. Wouldn't 3.42 be positive? Well, the quadratic is negative b, so this is b, right? This is, let's see if I do a different color here. This is, right, it's at squared plus bt plus c. So c is negative, which I made negative here to make this positive. But yeah, this should be, it should be negative 3.52, I think, right? I think that's right. So what do we get here? So the two answers I got were negative 1.67. I'll write them in order. So the negative root, when I use the negative sign here, I got negative 1.67 seconds. And the positive root was like 0.75, I think. No, 0.976. That's what I got. Yeah, Kelvin got the same answer that I got. That's good. So these are our two answers. I don't know how you write this stuff in mathematics. Something like that or something like that, right? And we're not going to take the negative number. We're going to take the positive number. Maybe that's obvious. Maybe it's not. I don't know. But time can't really be negative. Now, I will say one thing that can happen in this kind of problem that you got to be really careful about is you need to use your brain to kind of decide for yourself if that number is reasonable. Okay? And the way I do it is this. We know that these both solve our problem, right? If time could actually be negative, then this would technically also solve the problem, right? Would you all agree? I mean, it solves this equation. It's a correct solution to that equation, right? But what does that mean? So what that really means is that if time were to run backwards, what direction would the ball go? Go backwards, right? It would go back this way. Back this way. So what I like to think is that any type of motion like this, any projectile motion, it's technically a full kind of parabola, right? But we only have a part of the parabola right here. The reality is, let's see if I can fit this in here. Down here, something like that. The reality is that we've got this building right here, right? And the motion of our ball was basically just from here down to here. But this parabola, oh, that looks so bad. I'm so sorry. Ugh, it's just really hard to do this. I don't know. It kind of goes down like this, right? I'm just going to exaggerate it. I don't even care. It goes down like this, okay? But in reality, that projectile could have extended up to here and then down to here. I'm so sorry. This just looks awful. But so there's kind of two portions of the motion, right? And what it's saying is that if this was an object that had been launched from over here and thrown this way, you could break it up into two segments where the time from here to here, which is the time that we care about in our problem, would be 0.976 seconds. and the time from here up to the middle right there would be 1.67 seconds. But it's negative, right? Because it's backwards in time, right? Because we know time is actually, in this case, going forward this way. Now, what do you notice about these two times? They're obviously not equal to each other, right? They're obviously not equal to each other. The 0.976 would be the smaller portion of this parabola, though. Can everyone see that? It's the smaller part of the parabola on the right-hand side over here. And it's the bigger part over here. So that's where your brain can come into it, right? So you can think about what's happening in the problem. You think, well, I know that this is parabolic motion. I know that I could think of a parabola kind of extending backwards to the left over here, off of the screen, back this way. And you say, well, if I were to break the parabola up such that I just look at the motion here, I would know it's already going down. It starts off going down in our problem, right? And so as a result, we're taking the kind of smaller portion of the parabola over here, which makes sense that it's a small number, right? And I mention this because if you're doing this problem and you mess up any of these negative signs, it doesn't matter which one you mess up. If you mess up a single one of these negative signs here, and I'll show you exactly what would happen. If you made this positive right here, right? If we had made this positive, our answers would have flipped. This one would have been negative, and this one would have been positive. You can try it yourself if you want to. I'm pretty sure I'm right, though, that if you make this positive, the negative answer is going to be the small one, and the positive answer is going to be the big one, okay? I'll go back to where we were. But if you mess up any of these signs right here, or let's say for the initial velocity, you put a positive number right here, and you go through the calculations, it's going to flip the signs and you'll get the wrong answer. So just keep that in mind when you're doing your homework. If you want to kind of check your answer before you actually do it, don't just blindly pick the positive one. Make sure that the positive answer actually physically makes sense. Did that all make sense to everyone? Hopefully it'll make maybe more sense when you're doing the homework. I don't know. Okay. Just realize that the negative answer is not, it's not a real answer, but it means something mathematically. So, okay. Now our goal was to find this distance, though. We found the time, so let's refocus and actually get to solving the problem. So we know the time that it takes to hit the ground. So now we can figure out the distance that it traveled, right? Delta x. So let's do that. So now we can say that our equation for delta x is that delta x is equal to the x velocity times time. The x velocity never changed. Oh, you're telling me that if you make this one positive, that you're going to get a negative inside the square root? Are you sure? Did you calculate it? 4 times 5 is 20. 20 times 8 is... Yeah, it'd probably be negative. 20 times 8 is definitely bigger than 3.43 squared, yeah. So I agree with you, Chris. Maybe that one wouldn't work. But if you mess with some of the... Well, okay, that by itself would be an indication you've done something wrong, right? That's a good point. That if you do this equation, you get a negative inside of the root, you've definitely done something wrong, right? So that's definitely a good way to think about it. But changing some of the other signs... Actually, changing this sign would have done it, for sure. Right? That would have done it. Maybe it's just this one that... Okay. But getting right along here. So delta x, then, is equal to just 9.4 meters per second, which was what we found for Vx right here, by taking V initial times cos theta, and you multiply that times 0.976 seconds. That's it. In this case, you get 9.17 meters. Like that. Okay, that's a pretty straightforward problem. Anyone have any questions? So I have a bunch more problems here. And I think what we'll do is... This is a pretty good problem. I don't know. I think I'd rather do this one first, though. So let's take this one. Cut. Okay. The rest of these problems, I would say, are going to be quite a bit trickier. They should be pretty helpful to doing homework, I hope, because just the homework often, as someone had mentioned before, is pretty tricky compared to the stuff we do in class, so we'll do some tricky problems. That way you'll hopefully have an idea of the kind of way you want to wrap your mind around these things as you're doing them. Okay. So it says, a projectile is fired so that it just passes through the hole at point 1, as shown. So basically, you've got a projectile. It's fired at 80 feet per second at an angle of 63.4 degrees above the horizontal. It's launched so that it goes up like this, and it basically just exactly passes through this hole. And when it passes through the hole, it's going to make an angle of 57 degrees with this wall right here. Okay? And we want to find... Oh, wait, it got cut off somehow. This is x1 right here. We basically want to find the x and the y coordinates of the hole, as well as the time. Okay? The time is going to be the total time that it takes to go from here to the hole, basically. Right? All right. That's the problem. So, and to solve this problem, we'll do exactly what we did previously. We'll define a set of axes, x and y. So this is going to be the x direction. This is the y direction. We'll also then kind of set up our coordinate system, or set up our little charts. So in the x direction, we're going to have delta x, which is what we're trying to solve for. In this case, I'm just going to call this point right here to be 0, 0. So delta x is just going to be... Do I really need to have x1 and y1 here? I guess it's fine if we do that. We'll just call it x1. We'll have vx, which should be equal to... So we have 80 feet per second and an angle of 63.4, right? So this is our initial velocity. It's like this. This is 80. And we have an angle right here. That means we can break up our components like this. This is going to be vy initial on this side. This is going to be vx over here. If we call this angle theta, and we say theta is equal to 63.4, then we can say that, and, oh, this is feet per second. And we say v initial is equal to 80. Then we can say that vx is going to be equal to v initial times the cosine of theta. Plug in the numbers in. We get 80. Notice this is feet. We're going to have to change our acceleration due to gravity because of that. Because the cosine is 63.4. So vx is going to be 35.8. And time. That's one of the things we're trying to find, so we don't know that one. So we don't know what the x coordinate is to get to here. We don't know the time, but we do know vx. All right, let's do y direction. In the y direction, we've got our variables that are going to be delta y, which in this case is just going to be what we're calling y1. We don't know what that is. It's one of the things we want to solve for. We've got vy initial should be equal to 80 feet per second times the sine of the angle. So that's equal to 71.5. I'll write it just below it because I want to save some room. So vy initial is 71.5. Acceleration in the y direction. If everything's in feet per second, what's the acceleration in the y direction going to be? Yep, negative 32. Okay. And again, if you don't remember, this is the acceleration due to gravity when we use feet. Vy, we don't know what that is. That's going to be the y velocity when it gets to here. So basically, when it gets to this location, let's put a little vector on here. So we'll need that. So that's going to be our velocity vector when it comes out. I'll just call that one v. And, oh, no, just v. That's v. Okay, we don't know what that is. But vy is going to be a component of that. And then we got delta y, vy initial, ay, vy, the last one is time, which we don't know. You know, what I should really do, just to kind of simplify things a little bit right here. Whatever, I'm just going to leave it there. It's fine. All right, so how many pieces of information do we have here? We really just have two. We've got this one, and we've got this one. That's the only information that we really have, right? For the y direction. And in the x direction, really all we have is this piece of information right here. And I really do think if I just pull these things out of here, like we're gonna cut this out, we're gonna paste it up here, and then we're gonna cut this piece out, and we're gonna paste it up here. And I guess I'll put this part underneath it so it's clear what we did. Copy, paste. Okay. And the reason I want to do that is because I'd prefer to see all this information in kind of a more raw form, I guess, without all the calculations. Yeah. So can you see there we have very little information in this problem? We really can't do what we did in the previous problem. The previous problem, we also knew delta y. We used it to find time, and then we used that to find some other information. We don't have that going on here. In fact, we have a total of 3 unknowns now. Delta y is an unknown. T is an unknown. Delta x, that's 3 unknowns, basically, right? Feet? Did I write something in meters? Oh, that's in meters, isn't it? Look at that. Yeah. That should be feet. Sorry about that. If you were paying attention, Vx is, this should change to feet if you're taking notes or something. So what can we do? What other piece of information do we have that we haven't used yet? What's the other piece of information that's given in the problem that we haven't used yet? That's not a piece of information that's given in the problem, Tom. That's just an equation. But yeah, we can write that down if you want to. We can write here that x1 is equal to vx times t. That equation has 2 unknowns, right? We could also write an equation that would connect all of these together. Yeah, the angle, right? That's right, exactly. This angle, we haven't used this angle 57 degrees yet. And that should give us some information, right? Let's see what kind of information we can get out of that. So what I'm going to do is I'm going to draw a line. It'll let me. I'm going to draw a line like this. Right here. Maybe move this stuff over just a little bit. Make it smaller. I could move all of this stuff over, couldn't I? I think I missed the V, but we can fix that. So if I draw a line like that right there, I could say that the angle made, if I made that line straight, then this angle up here would be what? It's 33, is that right? Okay. And we can also say that this velocity vector now can be broken up into components, right? I can put a component if I want to for the y direction, and it would basically go straight down like this. That would be my y component of my velocity. And then I can do the same thing for the x direction. I can put an x component for the velocity like this. There we go. And I would say that this is basically v sub x. And on this side over here, we'd have v sub y. Now, how do I use that information to my benefit? Can I solve for vy? Do I know what vx is? What's vx equal to? What's the x velocity? Yeah, it's the same. It doesn't change, right? So if we know that this side is 35.8, and we know that this angle is 33 degrees, we can find Vy, right? Let's do it. So what do? We could write a tangent, right? We could say tangent of 33 should be equal to Vy over Vx, or just Vy divided by 35.8. So now we can solve for Vy by moving the 35.8 over here. So we'll get 35.8 at 23.2. Yeah, if you use negative, yeah, if you use a negative sign here, you'd get the answer. I mean, I guess we could do that. We could do negative, I guess, because then the answer will just automatically be negative, right? We can do that if you want. That's fine. Throw a negative sign in there. I was just gonna make it 33, and then I was gonna say that this number has to be negative because it's down. But yeah, that's fine. That works. Better, definitely better that way. It's consistent with what we did in the last problem, right? That's what we did in the last problem. Might as well do it here. So now we know that Vy is negative 23.2. And now we have enough information to find the time, right? So let's do it. Okay, so we'll do Vy is equal to Vy initial plus At. We want to solve for time, so we'll do Vy minus Vy initial divided by the acceleration is going to be equal to time. Vy was this, negative 23.2, minus Vy initial was this, 71.5, and we divide the whole thing by the acceleration, which is negative 32, and we get what the time is. It's one of the three things we wanted to solve for. So I get 2.96 seconds, as many people are putting. And then now that we know t, we can solve for anything else that we want to, right? So let's solve for y next. And we'll use this equation. So delta y is going to be Vy initial, which is 71.5, times the time, which is 2.96, plus 1/2, negative 32, times the time. We get delta y is equal to I got 71.45. We'll just call it 71 point. I'll call it 71. Because depending on how many numbers you keep throughout here, you might get something different. Something on the order of 71 or 72 feet. Something in there. That's what delta y is. And then the final thing to do is to solve for delta x. So x, here we had x1 was equal to Vx times t. So Vx is 35.8. Multiply by the time, which is 2.96. And we get 106, basically. There we go. We found time, x, and y. Does anyone have any questions? Let's see, how many more problems can we fit in here? Let's see. Because I want to have a lot of things for you all to look at. I think we'll save these two for next time. I don't even know if I can do both of these problems in 1 hour, but we'll try. And we'll do... this one's really good too. But I want to do this one, just because it's a common one I get a lot of questions about on the homework, so... There we go. Well, paste. Ah, yes. The loading screen for pasting, apparently. You know, I think it's time to go to the other to a new document, because this is just getting painfully slow. New page. There we go. This would be a lot faster. Okay, so here's the problem. you've got an airplane that's traveling at 100 meters per second in a level flight. So here's the airplane. It's traveling constant speed, 100 meters per second, in level flight with an elevation of 2,000 meters here. It spots a submarine on the water surface traveling at 20 meters per second in the same direction. So here's the submarine down here. It's going at 20 meters per second to the right. How far behind the sub should the plane be when it releases the bomb? And then we want to find the angle between the line of sight and the vertical at the instant the bomb is released. So we want to find basically this distance right here. How far behind the plane should it be when it launches its bomb? So the idea is that this plane has inside of it a bomb. It's traveling at a constant speed. It's going to release that bomb. The bomb is then going to hopefully undergo like parabolic motion and somehow hit the submarine, basically, like that. Any questions about the setup for this problem? Like what's happening? Our goal is to find this, basically, and to find this angle right here. All right. Okay, so the thing about this problem here that's important to understand is if I have an object that's traveling horizontally like this, and it has a speed of 100 meters per second, if you drop something out of the plane, the thing you drop, in this case the bomb is going to have exactly the same speed as the plane does. Okay? So effectively what's going to happen here is that when you drop your bomb, so here's our bomb here, what is its initial velocity going to be when we drop it? If all we do is we just drop it out of the plane. 100 meters per second, yeah, exactly. The same thing would happen if you're driving in your car and you took something in your car, like say you took a cup or something like this, and you held it out the window, you let go of it. If your car is going at 60 miles an hour, then the cup is going to start off going at 60 miles an hour too, basically. So what we have is we've got this bomb, and it's launched effectively forwards, horizontal, with an initial velocity that's equal to 100 meters per second. And what I'm going to do is I'm going to call this the x velocity, okay? So just as before, we're going to call this the x direction, and we're going to call this the y direction here. All right. Now our goal with this bomb is to make it hit a submarine, okay? But once we've released it, the bomb doesn't get to do anything. It basically is just going to undergo parabolic motion, and it's going to fall until it hits the water surface, okay? So let's draw the water in here. So it's eventually going to hit the surface right here. But we know some other things about this. We know that it starts 2,000 meters above the ground. So this distance is 2,000 meters, 2 kilometers. And what else do we know? That's pretty much it, right? So one thing that we could figure out is relative to where it starts right here, we could figure out how far the bomb is going to fall, right? We could figure out delta x right here. Now, at the same time that this is happening, there's a submarine, and it's moving to the right at a speed of 20 meters per second, right? So while the bomb is in the air, the submarine's also going to be moving at the same time, right? So we got to we have to take that into account somehow, right? But let's just go step by step right here. First of all, let's figure out just how far the bomb is actually going to move, and let's figure out how long it's going to be in the air, okay? So to do that, just as we've done before, we're going to set up our 2 sets of information here. We're going to have delta x. We don't know what that is. We don't know what the time is. But we do know that the x velocity in this case is equal to 100. And in the y direction, we're going to have delta y. What's delta y equal to? If I make this positive y, and I make this positive x, what's delta y equal to? that's right, negative 2,000. AY is going to be negative 9.8. We don't know the time. We don't know VY, but we'll write them down anyway. VYs don't know. Time, we don't know. That means we must know the other variable. And the other variable is the initial Y velocity. What's the initial velocity in the Y direction going to be? Of our bomb here. Yeah, it's 0. That's right. It's 0. So if the object is just released, it's just like if I take an object like this pen and I drop it, what's the initial velocity in the Y direction? It's 0. Oh yeah, it says to use g equal to 10, right? Okay, we can do that, I guess. I don't really like doing that, but we can. That's fine. It'll probably make the numbers work out pretty well. Thank you for noticing that. Okay, so we've got 2,000, negative 10, and 0. That's actually enough information to solve for whatever we want to. And what I want to do is solve for time first. Okay, so the time that it takes for the bomb to hit the water can be given by an equation that uses all of these variables but not Vy. And that equation is the one that we use very frequently, this one right here. So plugging in our numbers, we know that this is going to be 0. So all we really have is delta y. We know what that is. So it's, okay, we're solving for time. Let's solve for the time. So we're going to have delta y is equal to 1/2 ayt squared. So it'll be 2 times delta y divided by ay square root, should give us t, which means we do 2 times negative 2,000 divided by ay, which is going to be 10, negative 10. We square root this. Let's see. That's actually 20, isn't it? Square root of 400, right? So it's 20, yeah. So that's our time. 20 seconds. God, that seems like a long time, but I guess if you start from 2 kilometers up, it could take 20 seconds. Yeah, 2 kilometers is really high. That's much taller than any building. Okay, so that's our time. And we can solve for some other information now, because if we know the time here is 20 seconds, we can come back and we can solve for delta x, right? So delta x should be equal to basically vxt. So that's going to be 100 times 20. 2,000? Wait, really? That's the answer? Okay. I mean, it's not the answer to the problem, but it's not delta meters. Delta x. Okay. All right, so that's how far that this object is going to fly. But that's not what we wanted to find, right? Let's go back and look at the problem. So, airplane traveling at 100 meters per second. There it is. At an elevation of 2,000 meters, spots a submarine on the water surface. Now, the submarine is traveling at 20 meters per second in the same direction. And our goal is to figure out how far behind the sub should the plane be when it releases the bomb. Now, what we know is that after the plane releases the bomb is going to travel 2,000 meters in the air, no matter what, right? That's how far it's going to travel. So, where is the sub going to need to be if we want to hit it? Does it need to be exactly 2,000 meters in front of the plane? Does the sub need to be a little bit closer to the plane? Does the sub need to be a little farther away from the plane? Compared to the 2,000, I mean. So if we dropped, for example, if we dropped the bomb when we were 2,000 meters behind it, where would the sub be when the bomb hit the water? Would it be 2,000 meters? I guess I can ask the question again. Maybe that wasn't clear. So if maybe I'll write it down because it's complicated. So if we picked 2,000 meters here, right? We dropped our bomb. Okay. The bomb is going to go and it's going to basically hit at this location right here. Let's say. Is the sub still going to be at that same location? No. Right? Yeah, it doesn't account for the sub moving, exactly. So now I ask again, do we want to drop the bomb when the sub is closer to us or farther away from us? Closer. Yeah, exactly. So what we'd like to do is to say our 2,000 meters actually needs to go somewhere here. And what we want to do is we want to have the sub be right at that location whenever the bomb hits the ground, right? So the goal is to have the sub be right here whenever the bomb hits the ground, right? So what we need to figure out is how far does the sub travel? Maybe we call it x sub or something like this. How far does the sub travel, and what time interval do we care about now? How long is the sub going to be traveling when we release the bomb? 20 seconds, right? So the distance the sub is going to travel then, can you all figure it out? How far is the sub going to travel? If it's moving at 20 meters per second, that's 400 meters, exactly. So you take 20 meters per second for the constant velocity that the sub is traveling, and you multiply by 20 seconds, and you get x sub is going to be 400. You know, I shouldn't. I said I don't like doing this, but this is probably really worthwhile because then we can use numbers that make sense instead of like numbers like 9.67 and stuff like that that are. Yeah. So what that tells us then is if I want to find this distance, and I know that this is 400 meters right here, and this is 2,000 meters, then I think it's pretty clear to say that xd is going to be 2,000 minus 400. So the answer is you need to drop the bomb when the airplane is 1,600 meters. So that means this distance is 1,600 meters. That's when you're going to drop the bomb, basically, is when... Yeah. Okay. All right. So next thing to figure out was to find the angle between the line of the sight of the vertical at the instant the bomb is released. This could be kind of like your launch angle or something like that, if you want to think of it. Not like a launch angle, sorry. Like you could line up your sights to see it or something like that at this angle. And to figure that, we can just do a little trick here. Got a right triangle. So the tan inverse... I can explain the 1,600, sure. The tan inverse of 1,600 divided by 2,000. I'm pretty sure that this is going to be 53 degrees. Okay, so the idea is this. I'm going to take some of these pictures. I don't know. I don't know if I want to do that. How about I do this? Copy, paste. Let's just take this, go down a little bit, and I'll explain now that we have all the information. So here's what we know. Ton. What we know is that when we release our bomb, what it's going to do is it's going to travel to here. So let's extend our water. The bomb is going to travel and it's going to impact right here. Right? And we know that that distance is 2,000 meters. Now what the question asks is, how far behind the sub should the plane be when it releases the bomb? Right? So since the sub is moving, the sub is also going to be right here at that time. The sub and the bomb are going to meet up with each other here. Hudson, I'll answer your question in a second. Maybe I probably did it wrong, actually. Oh, I definitely did it wrong. Well, anyway. So that distance is 2,000 meters. And we figured out that in the 20 seconds that elapse, the sub is going to move 400 meters, right? So then this distance has to be 1,600 meters. Did I answer your question, Tom? Oh yeah, because this is I was thinking this is 25. I'm sorry. So it's 16 over 20 is, isn't it 4 over 5? Am I crazy? I'm probably wrong. Yep, I'm wrong. Completely wrong. Oh, I know why. God, I'm being silly. 38.7? That what you got, right? Yeah. It is 4 over 5, but the problem is that it's not the hypotenuse. I was thinking it was a 3, 4, 5 triangle, but it's not a 3, 4, 5 triangle. It's a 4, 5 something triangle. It's a 4, 5 square root of 25 plus 16. I don't know what that is. My bad. Anyway, that's the answer, though. Yeah. All right. Anyway, yeah, so I guess this does make sense to you, Ton? Is that what you're saying? You figured that out? We're out of time. I can't really do another problem. What I could do is I could at least show you something to work on for next time, so you're ready, I guess. Could be one thing we could do. So I really want to do like 3 problems next time, so we may have like a little bit longer class. I really want to do all 3 of these. They're all good. And all of them, in some fashion, are going to show up on your homework, either on your lab manual homework, or they're going to show up on your Mastering Physics homework. So these are the 3 problems. This one, I very much apologize for the picture here. I lost my original to this, so that's all I got. It's a really good problem. And so these are the 3 problems that we're going to look at next time. Yeah, I mean, technically we have 3 hours of class on Thursdays. We meet Wednesday, sorry. I just hate using all the time because it's just too much. But I can always stick around at the end. So we'll try to solve all 3 of these. This problem in particular, you have a lab manual problem that is very, very, very similar. It's not exactly the same, but it's extremely similar. So what this problem involves is you've got some bad guys over here that are shooting a mortar, trying to hit a hospital, and you have some physics students that calculate the way to like intercept the mortar. So really, this is a double projectile problem. So you've got a projectile that's shot over on the right, a projectile that's shot over on the left, and they basically hit right here in the middle where all this stuff is drawn. And you're supposed to figure out some information about that. So this is double projectile motion. It's pretty good problem. And then we've got a problem where you launch a projectile and you have to figure out, is it actually going to get past this obstruction right here? So that's a good problem. And then the last one we'll do is you have a projectile that's launched from here and it hits here. And the thing about this that's tricky is that the projectile is launched from an angle that is not the same as the angle of the elevation here. So this gets kind of tricky. And yeah, so all this stuff is either going to show up on an exam, in your lab manual homework, or on your Mastering Physics homework. So good problems to do. Anyway, so like I said, I extended the homework that was due on Friday. If you didn't happen to finish it, then you can finish it up tonight. And the rest of the homeworks, I'm just going to make them do Mondays. It makes a lot more sense. Making them do Friday is probably just too much. Anyway, so that's all I've got for today. We'll actually finish at 5:05. And if anyone has any questions about anything, I'm more than happy to stick around and answer them. You have a lab manual homework that's due this week, so make sure you get that turned in. You can turn it in later this week if you need to. It's not a big deal, but just make sure you get it turned in this week. And if you do have questions about that, I'll stick around and be happy to answer them. I spent a lot of time last time talking about how to solve the bead problem, but you finished it already, Paige? Good job. That's great. So thanks, everyone, and hope you all have a nice afternoon. See ya.